Here in week 4, we're going to take a look at probability. In order to move on with statistics, we have to have a really comfortable working understanding of probability and what are called probability distributions. And that's what we're going to look at over the next several weeks. This week, we're just going to take an introductory look at probability, what it means, and how we can use it. So first, what probability is. Probability really is the chance an event will occur. And we measure this chance on a scale. It's a number between 0 and 1. Now, 0 means it's never going to happen. The probability that I am going to make it to a conference in Seattle and a conference in Miami on the same day is pretty much 0. It's not going to happen. I can't be in both places at the same time. Now, on the opposite end is a 1. It's something that will certainly happen. The probability that the sun will come out tomorrow is 1. It's guaranteed to happen. And then in the middle would be 0.5. And that's equally likely that it will happen or it won't happen. We're at a 50-50 split. And the classic example is flipping a coin. You got about a 0.5 probability of a heads, 0.5 probability of a tails. If you're having a child, about a 0.5 probability it's a boy, 0.5 probability it's a girl. 0.5 is right in the middle. And then you can tip the scale either side. 0.8 is more likely, 0.2 is less likely, and you can go as many decimals as needed. Now there's a lot of important vocabulary that goes along with probability, and we use these a lot, so it's good to be aware of what they are. The first is an experiment. That's a process that's going to produce an unpredictable outcome. Let's say I'm interested in a certain employee, and I want to know tomorrow, is this employee going to be on time, early, or late? That's my experiment. I'm going to see when this employee comes into work tomorrow. Another important term is what's called the sample space. It is a collection of all possible outcomes or results to an experiment. So if I'm looking at this employee, the sample space, the possible events are on time, early, and late. Those are all the possible results that can come out of this experiment. Now, an event is what actually occurs out of the experiment. Let's say the employee ended up being early. Early is an event that happened. Notice the sample space is a collection of all possible events. Some more vocabulary. When we're talking about events, we have some events that we say are independent events. The occurrence of one event is not going to influence the probability of the next event. And an example of this is if we're looking at two employees. One of them's driving in from the east, one of them's driving in from the west. Different commutes completely. The probability that John is late does not affect the probability of whether or not Sue is early. Those two events are completely unrelated. They are independent events. One does not influence the other. So the flip side is if we have a dependent event, the occurrence of one does impact the probability of the other one. An example of this is if John and Sue lived near each other and they were coming into work, an accident on the freeway that they both have to pass is going to influence both of them. So if John is late, Sue probably would be late too. If John is early, Sue probably could get to work early too. There's a relationship there. The occurrence of one influences the other. That's a dependent event. I don't want to confuse independent events where the probabilities don't influence each other with what are called mutually exclusive events. These are two events that cannot occur simultaneously. Both of these things cannot happen together. You can't be both late and early. They're mutually exclusive. There's no overlap. There's no way to do both at the same time for the same shift. Now, when we're calculating probability, there's technically 3, but really 2 common ways that we look at probability. The first is what's called classic probability. And this is simply the ratio of the number of ways an event can occur compared to the number of possible outcomes. And so you often see it expressed as a fraction, the number of possible ways what we want, E, to occur, and we put it over the number of possible things that could possibly occur. Relative frequency probability is really similar. It is based on an experiment, though. So instead of just saying there's a coin with heads and tails, I'm going to flip this coin 1,000 times and see if it really is a 50-50. It's the ratio of the times the event actually occurred to the number of trials run. Both of these are really similar, though. The desired events are in the numerator, and all possible events or trials are in the denominator. Because we want our probabilities to be a decimal between 0 and 1, for this course we are always going to divide this fraction out to get a decimal. So let's play with some of this vocabulary and probability concepts. Let's define a sample space. Let's say we do a survey of a small focus group. We've got 3 people. We want to see if these 3 people approve of this new product that we're developing. It's in the testing phase right now. Well, we can start to look at what are the possible results of the 3 people. Well, the first person and the second person and the third person, they can all say yes, they approve. Well, they all could say no, they don't approve. Maybe we get a yes, no, yes. Boy, this is starting to get confusing. How many more possibilities are there? Just listing them out in a table like this sometimes can get us in trouble because we might miss one. So we need a bit of a better method. That better method that we're going to use to help us define the sample space of all 3 survey responders is what we're going to call a tree diagram. And the idea of a tree diagram is we start over here with the first person who can say either yes or no, taking us 2 different directions. Once we go those 2 different directions, though, the second person is going to branch off from here with either a yes or a no. In fact, that happens regardless of the first person's answer, branching off with either a yes or a no. And then the third person can branch off from each of those with either a yes or a no. And that kind of illustrates all of our possible results. The person could say yes, second yes, and a third yes. So a yes, yes, yes response. Going down the branch, yes, yes, no could be another response. Or how about yes, no, yes? And we can continue this all the way down the chart, and this gives us our entire sample space, all the possible results, all the possible outcomes. And once we understand our sample space, we're ready to address some probabilities. Maybe what's the probability, assuming every result is equally likely, what's the probability at least 2 people like the product? Well, there are 4 options here where we had 2 yeses. 3 here, 2 here, the first and the third, the second and the third. So there's 4 options from our experiment that turned out favorable out of 5, 6, 7, 8 options total. So 4 out of 8 from our experiment gives us a 0.5 probability that we get at least 2 yeses. Let's do another example. Back to our employee. He's either going to be late, on time, or early today, and we're going to give out a key promotion. Now, this promotion may or may not go to this employee we're looking at. And so we're interested, if he's late, does he still get the promotion? If he's early, does he not get the promotion anyways? So what are all the possible results from such an experiment? Well, to begin with, he could be either late, on time, or early. And then off of each of these stems, we can see that he could either yes, get the promotion, or no, not get the promotion. So our possible sample space, late yes, late no, on time yes, on time no, early yes, and early no. Here's another great probability example. Let's say Sears takes a survey of 817 customers. Now these numbers are made up, they're completely fictional, but let's say they take a survey And the customers, each of these customers just ordered a fridge, and Sears gets an extra kickback if they order a Kenmore, because that's Sears' staple brand. They also get a kickback if it's bought in store as opposed to online, and so they're interested in checking what are the probabilities here. So this table looks at that and organizes, of these 817 customers, online Kenmore purchases were 146. In-store Kenmore purchases were 192, which makes a total of 338 Kenmores. Other fridges, you got 264 bought online, 215 bought in the store. That's a total of 479. And if we total online, we get 410. Total in store, 407. And that gives us our 817 customers. So we've got our data. Now we're going to start doing some probability with this data. For example, what's the probability the next fridge purchased would be a Kenmore? Well, we need to know how many are Kenmores out of how many totals. So we want all the Kenmores, so we'll come over here to our total of 338 out of the 817 total. When we divide on our calculator, we get a probability of 0.4137. How about this one? What's the probability the next fridge is purchased online? Well, online, the total number of online fridges is 410 out of the total 817. Dividing that on our calculator, we get a probability of 0.5018. We'll usually round our probabilities to either 3 or 4 decimal places. How about this? What is the probability the next fridge is an in-store other purchase? So we don't want just in-store, we also want other. We want both of them. That's going to be the 215 out of the 817, or a 0.2632 probability. That's basic how we can calculate some probabilities. But I want to take this a step further and do a little bit more advanced probabilities. Based on that previous example we saw, there were 410 purchases online and 338 purchases of Kenmore, and 146 were both online Kenmore orders. I'm going to set this up with what's called a Venn diagram, where we draw some circles to represent each of the possibilities. So inside this circle represents all of the Kenmores purchased. And inside this one represents all of the online purchases, and you notice in the middle there's some space for the overlap. And we know there were 146 that were both Kenmore's online fridges. Now if I want to know how many were just online, we know in the entire online circle, all of them, there were 410 purchased online. Now we've already accounted for 146 in the middle, so when we subtract out the middle, we find out there are 264 that were purchased online, but not Kenmores. Similarly with the Kenmores, there were 338 Kenmores, but that includes the overlap. So when we subtract out the overlap, 338 minus 146, we find there's 192 Kenmores purchased that were not online, that were in the store. This idea of subtracting out the middle and subtracting out the overlap can really help us when we're trying to have two things occur at the same time. Let's take a look at that subtracting the double counted. The probability of two events. We want this to happen or that to happen. One of these two events. This or that. Or is the key word here. Or. The way we do that is we can take the probability of the first event plus the probability of the second event, but that's going to double count that center area of the Venn diagram. So we have to subtract the probability of both of them happening. subtract out the double counted, where they overlap in the Venn diagram. So for example, if I wanted to know what's the probability the next fridge is purchased either in store or it's purchased as a Kenmore. Well, let's look at those on our data here at the bottom. In store is this first column. There are 407 in-store purchases total. Going down to the total. But we're also interested in Kenmores. Kenmores, there are 338 total Kenmores. And so we could add those together. 407 plus 338 is 745. The problem is these 192 have been counted twice. That overlap is what we have to subtract out. So we have 407 plus the 338 minus the 192, the overlap. Do that first on your calculator to get 553 out of the total of 817. The key word here is or, tells us to add them together and subtract the overlap. When we divide 553 by 817, we get a probability of 0.677. This kind of opens the door to what is called conditional probability. Now, conditional probability is the probability an event will occur given some other event has already occurred. We have some new information. What's the probability that I need an umbrella when I go out today? You could probably assign some type of probability to that. But if I change that and say, what's the probability I need an umbrella given it's raining, now that probability has changed. It's probably increased the probability because it's raining. So I might be more likely to use an umbrella. The probability changes based on the extra information. That's conditional probability. And the formula we use for conditional probability, first off, a little notation, we use a vertical line. That means something is given to us. Whatever is after the vertical line, we assume is true. That's the sample space we're looking at now. The probability of A given B. The probability that I need an umbrella given it's raining. The way we calculate that is the probability of both of them divided by the probability of the given information. Notice the second part ended up in the denominator. So this is the probability I need an umbrella given it's raining, is the probability that I need an umbrella and it's raining divided by the probability that it is actually raining. Let's look at an example with some numbers. Let's go back to our Kenmore online in-store purchase. And I want to know what is the probability that a purchase was a Kenmore given it was purchased online. So first we want both of them. So a Kenmore purchased online, both of them happening at the same time is the 146. And we have to put that over the given number. So we don't divide by the total, we divide by the given information. Given it was purchased online. The online total is 410. So we'll take 146 out of 410, and that's 0.356 for our probability. How about this one? What's the probability a purchase was in store given it was not a Kenmore? So we start with both of them. Both of them, in-store and Kenmore. That's this number right here, in-store Kenmore, 215. And we divide by the given information instead of the total. Given it was not a Kenmore, it's one of these others. So we're going to divide by the 479. 215 out of 479 is 0.449. How about another example? Surveys conducted. How many magazines are read each month by a bunch of people? We want to read between 0 and 1, 2 and 3, 4 and 5, or do you read more than 6 magazines? So what's the probability that you read 2 or 3 or 4 or 5? Or. That or keyword tells us that we need to add the probabilities and subtract the overlap. So 2 to 3, we got 143 there, 92 in the next category. We're going to add those together, and then normally we have to subtract the overlap. But what's the overlap? Let's look closer at these two categories. Reading 2 or 3 magazines, and somebody who reads 4 or 5 magazines. These are mutually exclusive events. You can't read both 2 magazines and 4 magazines at the same time. You either read 2 or you read 4. There's no overlap between those. So with the mutually exclusive events, there's going to be no overlap and nothing to subtract. So we just have to add the 143 plus the 92 is 235 out of the total, which is at the bottom for us, 480. And when we divide, we get a probability of 0.490. But I'm going to tweak this example a bit, and we're going to look at a complement. No, I'm not telling you you look real nice today, although I'm sure you do. However, a complement in probability means the probability it did not occur. And the way we can calculate the complement of a probability is we take 1 minus the probability of the opposite event. Because you have to remember the probabilities of something happening is 1. If I flip a coin, the probability I get something on the coin is 1. And so I need to subtract out the probabilities of all the bad stuff that I don't want to include, and that'll give me the probability of the remaining event I'm interested in. Maybe an example with numbers would work better. What if I want the probability of reading less than 6 magazines? Well, that includes the first category, the second category, and the third category. In fact, it includes everything except the 11. This 6 plus, that's the complement. It's the opposite of what's being asked for. The opposite of what's being asked for is the probability of not getting 6 plus. So what we're going to do is we're going to take 1 minus the probability of that. 1 minus the 11 out of 480, which leaves us with 0.977. And that's a lot quicker than having to add up 234 plus 143 plus 92, getting an answer, and then dividing by 480. It would be even worse if there were 15 or 20 categories. And so a lot of the times it's quicker to subtract out what we don't want to get our final solution. Probability of 2 events. Now before we were looking at the probability of the first event or the second event. What's the probability it's a Kenmore or purchased online? We're talking about one single result with 2 possible events that satisfy that one result. Here we're talking about 2 events that we want to both occur simultaneously. And the verbiage you'll hear here is the word and. And this is different. And means I want the first event to occur, and also in addition to that, we want some other event to occur. And the way we do that is the probability of the first event times the probability of the second event given the first event already occurred. Here's an example. In a batch of 54 light bulbs produced on my manufacturing line, 3 of them are defective. I'm going to pick 2 of them randomly, and we're going to see if they're good. Well, the first one I pick, we're looking for good light bulbs. 3 are defective. So how many are good? 54 minus 3, the complement, is 51. There are 51 good ones out of 54. So I'll put 51 over 54, and then we're going to multiply. Once I test one good one, now the situation has changed because now there are only 50 good bulbs left. There were 51. We took one out and tested it. Now there's only 50 good ones left. Our total has also changed because there were 54 bulbs. Now there's one less. There are 53 bulbs left. So the second probability, given the first one already occurred, is 50 out of 53 because there's fewer light bulbs and fewer good bulbs. And so when we multiply 51 out of 54 times 50 out of 53, we end up with a probability of 0.891. Let's play with this example a little further. Let's make it a tree diagram. And one nice thing about tree diagrams is if we have our individual probabilities, we can multiply the probabilities down the branches to end up with the final probability. So first we split off. The first bulb could be good. There's 51 good ones out of 54. Or it could be bad. There are 3 bad ones out of 54. Then we select a second bulb, and so we need a second chart on here. And the second one could be either good or bad, but remember we've already, on this branch, picked a good one. So there's one less good one, 50, out of one less total, 53. However, if the second bulb is bad, there are still 3 bad ones in the batch. But the denominator still changed because there are fewer bulbs total. One has been taken out. On the bottom branch, we do much the same thing. Splitting into 2 sides, we could pick a good bulb on the second draw. There are 51 good bulbs out of 53 left to draw from. Or we could pick a bad one again. There were 3 bad ones. Now there are 2 bad ones left, because one of them's already been selected out of the 53 left to pick. So if we want our total probabilities of each outcome, to get our good outcome, we multiply 51 out of 54 times 50 out of 53. Good happens 0.891 of the time. For bad, 51 out of 54 times 3 out of 53, multiply the probabilities, and that happens 0.053 of the time. On the bottom half, we've got bad, good. For our next possibility, 3 54ths times 51 53rds is going to be about 0.053. And bad, multiplying 3 out of 54 times 2 out of 53 is 0.002. And we have a little round off error in there. But now we've got the probabilities of all the possible outcomes of drawing those 2 light bulbs. These tree diagrams with probabilities are going to be real nice in just a minute when we get to what's called Bayes' theorem. Bayes' theorem is a way we can calculate conditional probabilities given some information we know about our population. It's based on our definition of conditional probability that we had earlier. The probability of B given A is the probability of both of them happening divided by the probability of the second one, the given information. Well, this given information can be broken into several parts. It could be broken into the probability that A occurs, given B occurs, plus the probability that A occurs, given B doesn't occur. If you notice, the difference is in the given information, either B happens or B doesn't happen. That covers everything. Well, this formula stuff might be a little confusing. Let's look at a tree diagram, and it's going to help clarify how we use Bayes' theorem, given a bunch of information, how we can calculate another given probability. It's estimated that 20% of taxpayers file an incorrect return. 10% of the time, the IRS claims there is an error, but there actually is no error. And 30% of the time, they claim there is no error when there actually is an error. Now, there's a lot of probabilities in there as I make this a little smaller so we can fit a tree diagram on here. Let's see if we can break this up into a tree diagram. Initially, we're filing a tax return. It was either done correctly or incorrectly? We are told 20% are incorrect. So incorrect, 0.2 is a decimal, is the number of incorrect returns. The other half of the tree, then, has to be the complement, or the opposite. If 20% are incorrect, then the correct returns must be 0.8. Notice we get that by subtracting from 1. 1 minus 0.2 is 0.8. But there's a second situation that we're looking here that branches off. And I'm going to start on the bottom because that's what they're going to tell us about. 10% of the time, the IRS claims there is an error when there is none. So there's no error. It's been done correctly, but the IRS claims there is an error. Notice the path is, it's correct, but they claim there's an error. The complement, the other half of the branch then, is if they claim there is no error. Well, if they claim there's an error 10% of the time, 1 minus 0.1, they claim there's no error 0.9 of the time. We also have information about the top branch. If the tax return is done incorrectly, 30% of the time the IRS claims there is no error when there is one. So there is an error, and they claim there is no error 30% of the time. The complement of that, 1 minus 0.3, which means they claim there is an error 0.7 of the time. Building this tree is very important to help us visually see and multiply down the lines to get our probabilities. 0.2 times 0.7 is 0.14. 0.2 times 0.3 is 0.06. Going down the south part, 0.8 times 0.1 is 0.08. 0.8 times 0.9 is 0.72. As we set up these diagrams, I want to notice something. Each pair adds to 1. 0.2 and 0.8, that adds to 1. 0.7 and 0.3, that adds to 1. 0.1 and 0.9, that adds to 1. Each pair adds to 1 because they're complements. Also, our final probabilities, if you add them up, will also add to 1. 14 plus 6 is 20, plus 8 is 28, plus 72 is 1.0. We're going to use this to calculate some probabilities now. So we know this information. My business files my taxes, and the IRS claims we have an error. What is the probability that there actually is an error in my tax returns? What's the probability I actually have to be worried given the IRS claiming I have an error? Well, first I want to look at the sample space. The IRS claims I have an error. This is true. The IRS has done this. There's no doubt about that. So my sample space is wherever there is a claimed error. Up here there's a claimed error. Down here there's a claimed error. Both of these make up the claimed error. What I'm interested in is what is the probability that it actually does. So where's my incorrect? Claimed error is right here. So this is my numerator. This is the probability that both happen. Incorrect and a claimed error is 0.14. The sample space, the denominator, is what we have to work to get, and we're going to add the 14 with the 8. So down here, 0.14 plus 0.8 is 0.22, and 0.14 divided by 0.22 is 0.636. And so that's the probability that I actually have an error if the IRS claims I have an error. So notice how the tree helped us see that. The given parts make up our denominator. We have to add those together. And the overlap gives us the numerator. Let's look at another example, see if we can make this a little more concrete. There's a 60% chance your customer is going to request a second presentation after your initial presentation. This is common. Often they do so. If it is known that 70% of your successful bids get asked for a successful presentation, and it is also known that 50% of successful bids do not get asked for a second presentation. So just because you don't get the second interview isn't bad. You're just down to a 50-50 chance. But you got the bid. Good job. But what is the probability you had to make a second presentation in order to get that bid? Let's make this smaller so that we can actually make this into a tree diagram. So to begin with, we've got two options. Either you got the second presentation, which we know has a 60% chance, or you didn't. You didn't would be the opposite. 1 minus 0.6 is 0.4. But with each of those options, there is a chance that you did or did not get the bid. 70% of successful bids get asked for a second presentation. So that's up here. 70%, 0.7, got the bid. The opposite, 1 minus that, 0.3, did not get the bid. Looking at those who did not make a second presentation, 50% did not get asked for a second presentation of successful bids. So got the bid, 50%, 0.5. Did not get the bid, 1 minus 0.5 is 0.5. So to calculate our probabilities, 0.6 times 0.7 is 0.42. 0.6 times 0.3 is 0.18. 0.4 times 0.5 is 0.20. And 0.4 times 0.5 is 0.20 again. Notice each grouping adds to 1. And if you add all four of our final probabilities, they'll add to 1. It's a good sign, a good check that we did everything correctly. Now what we know is we've been given that we got the bid. That's given to us. That's a guarantee. So I only need to look at the stems here that got the bid. In this case, the top stem got the bid, and this third stem got the bid. That's our denominator. We're going to add those together. 42 and 20 is going to be 0.62 in our denominator. The numerator is the probability that I made the second presentation. So second presentation and the bid, that happens to be this one. So that 0.42 goes in the numerator over the sum. Adding the two parts together in the denominator gives us 0.42 over 0.62. There is a 0.677 chance that I had to make that second presentation. Notice how the probabilities changed with the given information. Initially, there's a 60% chance I have to make the second presentation. But given the extra information, given that I made the bid, I got the bid, the probability increased because I was given extra information, 0.677. So we've looked at a lot of probabilities here. I just want to summarize these formulas that we saw. The probability of an event is simply the number of ways the event occurs over the number of possible outcomes. And as we played with that, we found a couple options, some formulas in there. One is if we wanted option A or option B. The key word there is or. If we see that or word, we're going to add the probabilities together and subtract the overlap. If the key word we see is this vertical line, it means given. We're given extra information. Probability of A given B. We take the probability of both and put it over the probability of the given piece. A complement, we can take 1 minus the probability an event did not occur to help us calculate an opposite probability. This is often easier than manually figuring it out. The probability of A and B, now the key word is and, is a multiplication problem. The probability of A times the probability of B given that A has already occurred. And this setup Bayes' theorem, which was this weird formula that's really hard to make sense of. It's much easier to do Bayes' theorem with a tree diagram. And so that's what I want you to do for the homework assignment today. So these formulas are the important ones for today's assignment. Good luck to you on it, and let me know if you have any questions.